Hi, everybody, and welcome back. This is Mr. Gallagher here with Precalc for today, and we are going to be discussing Section 12.2, Evaluating Limits Algebraically. So if you remember last week, we talked about limits, and we looked at the graphs of those limits to see if we could visually describe the limits as a graph approached a particular value, whether or not there was a value for that particular x value, whether or not there was a y value that it evaluated to, whether it was a hole or whether there was a break in the graph. We looked at different ways of evaluating that. Well, today we're going to look at how to evaluate those limits without graphing them, just by doing them algebraically. And there's actually quite a few ways to do this, but we're going to focus on a few key ones for this section. So the first method for section 12.2 that we're going to talk about is just simply direct substitution. Now, direct substitution means I'm going to plug a value right into my graph. So for instance, let's say I'm looking for the limit as x approaches 3 of this particular function. It's going to be 2x cubed minus 6 over x minus x cubed, or x squared, sorry. So what could I do? Well, I don't know if there's actually a value for this or not, but what I can do is I can just plug in the value of 3 and see if it works out, because it might be a continuous graph at this point and I don't have to worry about it. So when I plug that in, the limit of that is going to be equal to 2, and then 3 to the third is 27, right, minus 6 over x, which is 3, and then minus x squared, 3 squared, which is 9. And that means my numerator is going to be what? That's 48. And then my denominator will be negative 6. Well, that actually evaluates to be negative 8. And that is my limit. That's also what is f of 3, right? And because we can just plug it in and it looks like it's going to be a continuous function, the limit as x approaches 3 from both sides is going to be negative 8. And that's just using direct substitution. That's the easiest way. It would be nice if every problem worked out where we can just use direct substitution, but that's not always going to be the case. We saw last week on a problem where we couldn't plug it in, so we had to look at numbers just to the left and just to the right of it, right, to see if we get closer and closer, and then the graph actually kind of gave it away as to what the value would be. So another way we can evaluate the limits is going to be by factoring. And what do I mean by factoring? Well, let's look at another example. Let's say I have the limit as x approaches negative 4 of this problem. I've got x squared minus x minus 20 over x plus 4. Well, this is one of those like we saw last week. I can't just plug in negative 4 here because I'm getting a 0 in the denominator. Can't divide by 0. So if you remember, we actually looked at numbered a little bit to the left and a little bit to the right, and we kind of estimated if I plug in like negative 3.999 and negative 4.001, I got really close to it. But another way I could do this, rather than just by trial and error, is by actually factoring. So let's factor the numerator here, and that's going to be, what, x plus 4 times x minus 5, right? And that's going to give me that negative 20. And then at the bottom, I still have an x plus 4. Well, this x plus 4 and the other x plus 4, these both can cancel. Right, so now I'm left with an equivalent function of x minus 5, right? Well, I have this limit as x approaches 4 of x minus 5. If I graph these will be the same. But do you remember when we did rational functions, we said there might be a hole, and this actually is the hole. Where's the hole going to be? Well, I can plug in negative 4 now and get negative 4 minus 5, and that's going to give me this is the limit. Let me rewrite this. The limit as x approaches negative 4 of x minus 5. Well, I can just plug in negative 4 for x and get negative 4 minus 5, which is negative 9. And that's where there's a hole. The hole is going to be right at negative 4 and negative 9, right, as we saw before. And negative 9 is also going to be my limit. And because I'm approaching negative 4 from the left and from the right, I'm getting closer and closer to negative 9 as a y value. That's going to be the limit as x approaches negative 4 from the left and from the right. It approaches that hole. So the limit's going to be negative 9. Let's try another factoring problem. How about this? How about, we'll do it in a different color. How about the limit as x approaches 6 of this big function. I've got x squared minus 7x plus 6 over 3x squared minus 11x minus 42. So again, we could try direct substitution. I'll save you a little bit of work. If you try to plug in, that's not x minus 6, it's x approaches 6. If you plug in 6, you're going to get a 0 in the denominator here. So let's go ahead and factor. The top factors to be what? That's going to be x minus 6 and x minus 1, right? Because that gives us negative 7 as that middle term. And then on the bottom here, I'm going to have a 3x and an x, and I'm going to have a minus 6 and a plus 7 here when you unfoil that factor. And then what do we notice? Well, we notice that the x minus 6's can cancel, and I'm going to be left with this function, x minus 1, write that a little bit better, x minus 1 over 3x plus 7. So now that's an equivalent function, right? I just simplified it, and just like we saw in rational functions, that means there's going to be a hole there. So I'm really looking for the limit as x approaches 6 of the function x minus 1 over 3x plus 7. Well, now I can use direct substitution, and I'm going to plug in 6 for x, so I get 6 minus 1 over 18 plus 7. So I get 5 over 25, which simplifies to 1/5. And that is going to be my limit because there's going to be a hole at the coordinate 6 comma 1/5. And so 1/5 is going to be the limit as x approaches 6 from the left and the right. The limit is going to be equal to 1/5. And that's how you can do our limits by factoring. We're going to factor out a common term, cancel, and then hopefully use direct substitution. Okay, one other topic I want to talk about, and I'm going to go to a new page on this. I want to talk about limits at infinity. Meaning as x approaches infinity or as x approaches infinity or x approaches negative infinity. We did this already with rational functions, so a little bit it's kind of familiar, but let's just look at polynomials. So if I have the limit as x approaches negative infinity of this function, x cubed minus 2x squared plus 5x minus 1. Well, if you remember with rational functions, whenever we're looking at the limit as x approaches negative or positive infinity, all I care about is this first term with the highest exponent. And an easy rule of thumb is, say, well, if I'm approaching negative infinity, what will happen if I plug a large negative number into this function, into this term? Well, I'm going to get a large negative number. So this limit is actually going to be equal to negative infinity, because as x gets larger and larger, closer to negative infinity, that x cubed is also going to become a very large negative number. So we're looking at only the term with the highest exponent. So this one, my answer is going to be negative infinity. What about this one? How about this? What about the limit as x approaches infinity of this function? 4 plus 3x minus x squared. Be careful. What's the term with my largest exponent? The term with my largest exponent is this negative x squared, right? So I'm not going to worry about these other terms. Just like I didn't worry about these up here, I'm not going to worry about those other terms. I'm just going to look at the negative x squared term. Well, what happens when I plug in a very large number into negative x squared? What do I get? Well, I square it, which makes it positive, but then that negative makes it a very large negative number. So the answer to this is also going to be negative infinity, right? Because I plug in a very large negative number, and as a result, and the negative sign is going to make it negative, so my answer to this is going to be negative infinity. Let's try one more. What about the limit as x approaches negative infinity of 5x to the fourth minus 3x? So again, I don't care about those other terms. I just care about this guy right here, that 5x to the fourth. What's going to happen when I plug in a very large negative number, because it's negative infinity? Well, when I raise it to the fourth power, it's going to become a large positive number because it's an even exponent, right? So a large exponent, or large number raised to the fourth power is going to be positive. times 5, still going to be positive, so it's going to be a large positive number, so my answer is going to be infinity. So again, looking at the first term and then looking at the exponent, whether it's an even or odd, and then if I'm approaching negative or positive infinity, to see where I'm going to go. And those are my limits at infinity. And then just to review, if you recall, we did our rational functions at infinity, and we had two examples of that we had looked at from a previous section. I just want to kind of review that here. So do you remember the first example we had is when we had a rational function where we had powers equal, right? And what do I mean by that? Well, if I'm looking for the limit, and this is our end behavior we looked at of our rational function graphs, or if I had the limit as x approached infinity of this function, 4x plus 5 over 8x minus 3. How do we do that? Well, if it's powers equal, right, because that's to the first power and that's to the first power. So this means the degree of each are equal. The numerator and the denominator have equal degrees. Then what do I look at when I'm trying to get to the limit as x approaches infinity? I'm looking at the leading coefficients, right? And this is going to be 4 over 8, which is 1/2. So there's going to be a horizontal asymptote at 1/2, and that's going to be the limit as x approaches infinity. So whenever I have powers equal, I'm going to look at the leading coefficients. The other example we looked at is, what if I have a bottom heavy function? Well, a bottom heavy function such as this, what if I look at the limit as x approaches negative infinity, and I'm looking at 6x squared minus x over 3x to the third plus 1. So this one's bottom heavy, meaning in this one the degree of the denominator is larger than the degree of the numerator. That's what we call a bottom heavy rational function. Then what's the limit of this always going to be? The limit's always going to be a horizontal asymptote at 0. So as x approaches infinity or negative infinity, this function is going to get closer and closer and closer to 0, because the bottom number is always going to be bigger than the top number. And that's it. That's how we do our rational functions at infinity, which we had learned before, but just kind of a recap. So what did we cover today? Real quick, remember we did direct substitution, plug a number in to find a limit. If we can't do that, we're going to try to factor it and then see if we can plug it in. And if we can, that means it's going to be a hole there, and we look at the limit as where that hole is going to be for the y value. Limits at infinity is we look at negative and positive infinity, and we look at the number with the largest exponent. And then that's very similar to what we do with our rational functions. Our powers equal and our bottom heavy functions, we have two different ways of determining those limits. Either for powers equal, it's the coefficients of the leading terms, or if it's bottom heavy, our limit's going to be 0. That's it. So I have an assignment for you. This is out of your book. This is not a worksheet this week. This is on page 754. And the numbers for that are going to be 3, 7, 11, 13, 23, 25, 35, 37, almost done, 39, and 43. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 problems. And check those out. These are all odd problems, so the answers are in the back of your book. So if you're having trouble working them out, look at the answers in the back. If you have any questions on these, please don't hesitate to ask on the discussion boards, or feel free to drop an email. Please make sure when you're done that you turn this in on the assignments on eCampus. That's it for today. Thank you very much. We'll talk to you next time. Take care.